Hello, this week we will talk of kernel methods, and as such we will make a review of linear discriminants. So as we saw last week, this is the equation of a linear discriminant. So basically we have the weights, wi, which is given as a vector here, but is expanded with the component of the vectors as wij, and the constant wi0. And in a linear discriminant, we are computing the value of h as the sum of the products of the xj, which are the components of the vector x, with the corresponding weight wij for function hi, and this for elements from 1 to d, where d is the dimensionality of x and w. And as such, it gives us, I would say, a value. And we only use usually for classification the sign of that is returned by function h. So if h is giving us a positive value, we assign this to a class, and if not, we assign this to another class. So in two-class model, we only need one h. So we have one equation h. So when h is positive, x belongs to C1. When it is negative, it belongs to C2. And the weight in that model is determining the orientation of the separating hyperplane, because the configuration of our model with wi0 is basically cutting the space in two with an hyperplane that is cutting it. So one side of the hyperplane is the positive, it's for positive values from h, and the other side is for negative value for h. And the orientation in that space is given by the weight w. And the bias W0 determines the position of the separating hyperplane to in that space. It is basically the corresponding or proportional to the distance from the hyperplane to the origin at 0.000, for example, in 3D. So if we are looking at this in 2 dimensions, so we have our space in 2D, and we have this red line here, which is the separating plane here, separating line, in fact, in 2D. So this line is separating everything in there. So on one side, we are in the case where h is positive. On the other side, this is the case where h is negative. So whatever x on one or the other side, according to the sign given by the application of h on it, we have one case or the other case. And the separating line here is in fact at the point where h is equal to 0. Now we can see that w here is basically giving us the orientation of that plane. So with different w values, we have different vector w, and the separating frontier, separating line here is perpendicular to w. And finally, the distance between the origin here and our plane, in fact, the smallest distance is given by w0 divided by the norm of w. So if w is unitary, we can constrain, or we can normalize w to be unitary. It will be basically w0 that will give us the distance, the smallest distance of the hyperplane to the origin. Otherwise, we need to normalize with the norm of w. And if we are looking at a given x, in fact, that x, the minimum distance of that x from the separating plane, is given by the absolute value of h applied to x divided by the norm of w. So if w is unitary, then the h is basically giving us the distance from our x to the plane. So we saw last week the Perceptron criterion. Basically, it states that if we take all misclassified samples, so this ensemble, this set big Y is giving us the elements of X that are misclassified. And then we are making a sum over all these misclassified items, and we are multiplying the value of H over XT times the corresponding label, which is either -1 or +1. And that gave us the error to use. Of course, an error, we want to minimize it. So given that we are in a minimization case, And even more that misclassified samples are basically cases where the sign of R and H are not the same. So the product of R and H here for all misclassified sample is always giving us a negative value. We are applying the minus sign over that. So that gave us the Perceptron criterion. So this is an historical, interesting criterion, but this is in practice not working really well. First weakness is that the link between the error and the nature of the error is not really obvious, not really strong. So if we are facing, for example, non-linearly separable data, the classifier is likely to diverge, likely not to converge into anything good. So it will not be able to deal at all with non-linearly separable data. So an example of non-linearly separable data set with 4 instances, 2 from the class of red crosses, 2 from the class of blue stars. We have this point here, and these are not linearly separable. It is impossible to have a line, a straight line that will get us with a 100% accuracy, so zero errors here. We will necessarily make at least one classification error with separating hyperplane. So if we apply the perceptron here, we can see that at iteration 20 we have that thing, and at 40 it goes there, at 60 it goes there again. So it's kind of moving in between some positions. It seems to be diverging. In fact, it seems to be oscillating between different positions that are not good at all, and the error is relatively high. So it's not working well in that case, and the criterion is not really good. So now we are looking at least squares criterion, which has also been presented last week, where we will use a different criterion, which is the one that is usually used for regression. So we are looking at a criterion of regression, where we are computing the difference between the target. Here we assume the target is -1 or +1. And we also have here the value of H. So basically, H is the linear discriminant. So we kind of convert this from a summation to a vectorial product. So W transpose XT. This difference is squared. So we have this at the power of 2. We are summing this over all data instances, not just those who are misclassified divided by 2. So half of that. So this gives us a very classical criterion used for regression, but now we apply this to classification. So it tends to minimize the distance from the value of H over X to the RT value. So compared to the perceptron, it is certainly much better. It manages much better non-linearly separable data. So we are progressing toward having better criterion. It is putting emphasis on data that are far from the separating hyperplane. And this thing is not necessarily the right thing to do. Usually, if we have the data that is far away, that is correctly classified, it is not that much interesting. We usually care of the data close to the frontier. So it's kind of not doing the right thing for this, although it is kind of better than perceptron. So if we are looking at this applied to the same non-linearly separable data, we have this thing, and so we are optimizing something that goes in that direction. That's good. Up to some point, that's at least better than perceptron in the sense that it is converging to some results. Even though the error here, we still have 2 samples misclassified. So basically, we have an accuracy of 50%. We can have done better than this by having only 1 sample misclassified. But it seems to be converging to some kind of stable placement in between the data. So it's kind of far away from the data, but still well positioned. What we can understand here is that these samples are misclassified because they are those who are the closest to the separating hyperplane. So the corresponding error is lower than those we can get if we are kind of inverting the decision and misclassify those ones who are actually well classified. So those are well classified because they are the furthest away. And given that they are the furthest away, their impact on the error is highest. So it's better to get them well classified than the 2 first here, which are closer to separating hyperplane. But still, the least square criterion is not perfect. It's better than Perceptron, but it's not great. So we need to get something better.